Thank you. So I emphasize that this is supposed to be a introductory lecture, not just surveying things well known to people who work in the field. And I should say, I'm certainly not a field in which I feel particularly expert myself compared with many of the people here who will be talking over the next few days and weeks. Everything I say will be, it says nothing new, will be basically one of the old papers, which I just mentioned, called Gauge Theory in Higher Dimensions, in 1996 with Richard Thomas. And then part 2 in 2010 with Ed Siegel. Soon be time for part 3 one of these one of these years. And also another basic reference, of course, is Dominic Joyce's book, which also explains all this material systematically. So the first part of the talk, we want to just review the basic geometric objects of interest from this for us. And these will be of two kinds, with submanifolds of a manifold with G2, or with exceptional holonomy, G2 or spin 7 holonomy. So we assume we all know what that is, but perhaps we should review a bit more about gauge theory. It's to say, over our manifold M, which will have our special structure on it, we want to consider auxiliary bundle E. Think of, say, a complex vector bundle with structure group SUN, some n. And we want to consider connections on this bundle, which we can also think of as covariant derivatives. So we use the notation, the connection is giving a way of differentiating sections of the bundle. So these objects are less familiar, perhaps, than submanifolds, but they're actually much easier to work with in many respects. In particular, if we thought about the space of all submanifolds, that might be quite unclear what the right thing to do, whether you want to consider immersed or embedded, or do you want to consider parameterized or unparameterized. There's a straightforward, easy to write down notion of the space of all connections of our bundle. And this is just an affine space. If we have one connection, we get another one by just adding a one form with values in the associated bundle of endomorphisms of E, or rather the sub-bundle of that corresponding to the SUN structure. So if we have an A, one connection, we can consider another one, A plus little a, where little a is going to be a one form in, right, this symbol for the sub-bundle of ND corresponding to the Lie algebra of SUN, just the skew-adjoint endomorphisms. Then the other basic things to recall is that a connection has a curvature, f of a, which is a two form with values in this same bundle. And the third kind of object one wants to think about are the gauge transformations of the gauge group. G is equal to the automorphisms of E, preserving the metric structure. So the question we want to discuss in this first section is what are the particular things we can do in the way of studying submanifolds or connections on a base manifold M with exceptional holonomy. So we'll start with the case of 8-dimensional manifolds with holonomy spin 7. Although the title of our program is G2, and so that we want to really emphasize somewhat after a while the G2 case, in a way it's best to start with the sort of as you see, the kind of the father, you might say, of the G2 situation, where we consider, so let's consider X8, a manifold with spin 7 holonomy. Well, we had a lecture this morning by Spiro explaining the definition of this, the one point of view on the algebraic structure involved, and there are many different ways one could go about setting that up. I'll take a slightly different point of view here in terms of spinors. If we just accept that we know that spin 7, that's to say the double cover of SO7, has a spin representation. Spin representation on R8. So that's supposing this is the basic fact we want to assume known, the existence of spinors. And so what we mean by having spin 7 holonomy, it's not really, it's the group plus the representation, which is strictly involved in that description. So we mean that this is the representation of spin 7 involved. And what does this mean? This means that we get a map from the Lie algebra of spin 7, which is just the same as the Lie algebra of SO7. It's clear this is a injective map into the Lie algebra of this acts by orthogonal transformations to the Lie algebra of the orthogonal group in 8 dimensions, which we identify in the usual way with lambda 2 of R8. On the other hand, this has got dimension 21, and this has got dimension 28, so it has to be properly injective. So what we see is that we have a decomposition of lambda 2 R8 can be decomposed in a way invariant under spin 7 into the image of this map, which is a 21-dimensional space, plus a orthogonal complement, 7-dimensional orthogonal complement. So on our manifold, we can apply this invariantly to the tangent space at each point, and we can write the two forms as a sum of sections of the corresponding bundles. And so we can decompose our curvature of any connection in the corresponding way. Anytime we decompose the bundle of two forms on a manifold into pieces, we can decompose the curvature in the same way. So a spin 7, we get straight to the definition. A spin 7 instanton definition is one where the component in the 7-dimensional piece of the curvature is 0. So let's say pi 7 of f a is equal to 0 in obvious notation. This is projection onto that part. Right, so that's the definition. Those are the special connections that we have on an 8-dimensional manifold with spin 7 holonomy. We'll come back to say more about why this is a particularly good equation to consider in a few minutes. So this was all the this is the gauge theory. Sorry?
Could you repeat what an instanton is?
Well, this is just the name, just as a name at the moment. Actually, it's not a very good name because it's the name which has got into the literature. So just take it as a unit.
Instanton?
No, a connection A is a spin 7 instanton if it satisfies this condition. That's the precise statement. What is the submanifold story? So this was essentially mentioned in Spira's lecture. There's a special class of, what did he say? Oh, let's see, how do I say this? Not sure if he quite said it anyway. Very much related to things he was saying in his lecture. There's a special class of 4-dimensional subspaces of an R8 with structure group spin 7, which one can describe in terms of octonions and so forth, but we won't attempt to do that. Let's take a more. And this is also connected to a special 4-form that we have. So let's, actually, before we get to the submanifolds, let's talk about the 4-form. So this is called capital Phi by Spiro. We can define that from our point of view quite simply, that if we take an orthonormal basis with respect to the natural metric omega I, of this 7 lambda 2 7 component, then our 4-form we can describe as the sum of omega I squared. Maybe not quite sure about the factor to get fit with conventions. Perhaps 1/7 would be best. Anyway, so this is clearly this is a recipe for writing down a spin 7 invariant 4-form. From this decomposition, because from the orthonormality says that if we take a different basis, we don't change this form. Of course, this is the wedge. We'll write it that way. This is the wedge square. So connected, that's the 4-form. Connected to that, as we see, are these submanifolds. But I want to. I'll define these in the following not very geometric way. Let's consider a model for R8 with a spin seven structure. This will be a useful model for other purposes. Supposing we take 2 copies of R4, and supposing we have a fixed isomorphism, so these are supposed to be oriented R4s with Euclidean metrics. Suppose we have a fixed isomorphism compatible with all the structure of the self-dual subspace of one space with the self-dual subspace of the other space. So then we can write down a 4-form which is, so we take, say, coordinates xi on one copy and yi on the other. So we'll take the volume form in each factor. Plus in fact, I think minus the sign I got, the sum. So let's take a basis now, omega I, one standard orthonormal basis in this space, and the corresponding basis, say, omega primed I here, take omega I, wedge omega primed I. So these are not very good notation, because this is different from the omegas I was talking about before. Or more invariantly, if we think of this as, if we think of inside lambda 4 of this direct sum, we've got lambda 2 of one factor tensor with lambda 2 of the other, then using the metric to identify with the duals, this is just the object corresponding to the identity map, or under this isomorphism, another way of saying it. So this is a useful way of writing down what we've written down a 4 form on R8 in this fashion, which in fact, as the notation suggests, is a standard model for this special kind of 4 form which corresponds to these spin 7 reductions. And that's a useful point of view. Then we can define, one way of defining a Cayley subspace, a 4-dimensional subspace, inside R8, if it's one such that we can write phi in this form, and the subspace is the first factor, or the second factor. So so say L, say R8 is a Cayley subspace if the pair L phi can be written as this form in this way, with L corresponding to, say, the yi equal to 0, say. Let's go to R41, let's put it that way. Okay, so that's a way of defining what we mean by a, just in linear algebra, a particular linear subspace of this R8 with this spin 7 action, and then we get the corresponding notion immediately on a manifold, a 4-dimensional submanifold Q of our 8-dimensional manifold is a Cayley submanifold. If each tangent space is. At each point, the tangent space of Q is one of these special subspaces. Now, one of the salient points to notice about this is that if I restrict my 4 form to the subspace corresponding to L, just to this one, then it gives the volume form. Psi restricted to Q is equal to the volume form. In fact, as Spiro mentioned, which we won't quite, it's also true that this is a characterization of these, the restriction, if we take any 4-dimensional subspace, the restriction is always less than or equal to the volume form. The Cayley ones are precisely where equality holds. So what can we say about this? What kind of condition is this? So if we take this model, then we think of this, what are the automorphism group of this pair consisting of this data? We can rotate one R4 by any orthogonal transformation And then we can rotate the other R4, provided we rotate the lambda 2 plus component in the same way we decided by under our fixed isomorphism. So if, for simplicity, we think of covering SO4 as SO3 times SO3, with the action on the two lambda 2 plus and lambda 2 minus, then we can take product of two copies of SO3 from one factor and one copy from the other factor. So the automorphisms of this picture is a 9-dimensional group, locally isomorphic to 3 copies of SO3, product of 3 copies of SO3. Whereas, so if I take the spin 7 has got dimension 21, so the orbit of this picture under the action of spin 7 has got dimension 21 minus 9. Okay, the orbit has got dimension 21 minus 9, which is 12. So this tells us that the space of Cayley subspaces forms a 12-dimensional submanifold of the Grassmannian of all 4-dimensional subspaces in R8. So that's the Grassmannian of 4 planes in R8. It's got dimension, you take 4 times 8 minus 4, which is 16. So this is a codimension 4 condition. There are 4, at each point you're imposing 4 conditions on your tangent space for it to be Cayley. This is one good way, at least I find useful, to think about these unfamiliar structures, like these spin 7 structures on R8 and so forth, in terms of some model where you fix some extra structure, then you get a more familiar symmetry group. So one model is this split into the 2 subspaces. Another important model is to consider the subgroup SU4. Another model is to think about SU4 contained in spin 7. That's to say, we consider, suppose our X, our 8-dimensional manifold, has holonomy SU4, or in other words, is a 4 complex dimensional Calabi-Yau manifold. So everything we've done, we can do in particular in this special case. I mean, by a model, we fix some extra structure. How does that work? If you so there's a star operation from, say, the 0-2 forms to themselves, defined in a sort of obvious analogy to the star on a real 4-dimensional manifold. So this is defined by the condition that the Hermitian inner product of alpha and star of beta, alpha wedge star of beta, that's what I'm saying, is equal to the Hermitian inner product between alpha and beta times the complex volume form, the imaginary. So if you have a Calabi-Yau 4-fold, means you have a complex structure with a holomorphic form, say chi, let's call it. So this is a 0-2 form. These are 0-2. This is going to be a 0-4 form. So this is the sort of 0-4 part of chi. So times. So the significance of the Calabi-Yau condition, from the point of view of complex geometry, is that we have a holomorphic volume element. And given that, we can write down this definition, which is just like the definition you'd write down of the star operation on a Riemannian four-manifold using the ordinary volume element.
Are there? Is chi is 404?
What do I want to say? So I want to put chi bar, yes, that's right. Yeah, so it's always a, yeah, exactly, thank you. Yeah. Right, so chi is, that's right. That's what I want to write down. So beware, however, this is not complex, this is complex antilinear. And depends upon, we could multiply our chi by a scalar, a non-zero scalar, which sort of might think is a trivial change from the point of view of Calabi-Yau geometry, but that will change our definition of our star by a factor. But in any case, just as in the Riemannian situation, this star squared is equal to 1, if I got the conventions correct, and we have, so we can decompose into the eigenspaces plus and minus 1 eigenspaces of star, just like the decomposition of the two forms on an oriented four-manifold. But I say beware, these are real. So this is a complex six-dimensional space, and these are real six-dimensional spaces. Multiplying by I takes one to the other one. So how do our definitions look in this special case? First, what is the lambda 2,7 space? It's just so lambda 2,7. So there's always a bit of a. Perhaps we should say we take the real. We take. So these are complex forms, but we can, if we take one of these plus its conjugate, we get a real form. So suppressing that convention, we can write this as equal to lambda naught 2 plus direct sum, the other obvious form we have, the multiple of the Cayley form. So this is one-dimensional, and this is six-dimensional. In fact, you can think of it, SU4 is actually locally isomorphic to SO6. Well, perhaps it's precisely equal to spin 6. Isomorphic to spin 6. So you can think of, so we're thinking of our original spin 7, at least going down to SO7, this is its action on a seven-dimensional vector space. Reducing the symmetry to SU4 fixes your one dimension and reduces you to the spin 6 inside spin 7. So that's another point of view. So you have an analogous thing on a four-manifold where if you reduce the holonomy to U2, then the space of self-dual forms splits into the real part of the 0-2 forms and the Cayley form. So this is a kind of the same kind of thing. In any case, with that at hand, we can say, what is our spin 7 instanton equation? It takes two forms, it takes two components. First, that the F02 plus is equal to 0, just the analog of the self-duality equation, and then that this component is equal to 0. Let's write it that way. In particular, a particular kind of solution would be when the whole F02 is equal to 0, and this just corresponds to having a bundle compatible with a a holomorphic structure over our complex manifold. What about the submanifold story and the 4 form? First of all, the 4 form in this model can be written as a combination of the obvious forms you have around, which are, I just have to make it up. What have we got? We got omega squared, a factor of 2, and then I got plus, Harvey and Lawson had minus, the real part of our holomorphic form, which we call chi. What's a basic example where we also have this kind of model, an example of a subspace? In fact, there are 2 basic examples in this complex situation. We can either have a Lagrangian subspace, a totally real subspace. So in other words, one model is when we have standard complex coordinates ZA is XA plus I YA. So these are the real and imaginary parts in C4. The other model is when we take C2, direct sum C2. As you can write down. If you write down the standard sort of forms in these coordinates, you write down that form in these coordinates, you should get this expression with right tweaking of the constants if necessary. So what that says is that particular examples of these Cayley submanifolds, if you're considering an 8 manifold which is actually got SU4 holonomy, there are 2 kinds of particular examples which are sort of familiar. One are what are called the special Lagrangian submanifolds, which are Lagrangian with respect to the symplectic form, and where the holomorphic, the real part of the holomorphic form is the volume form, and the other are the complex, 2-dimensional complex submanifolds, the other kind of example. Right, so that's all we're just in 8 dimensions, so we
Calabi-Yau 4-fold has 2 different spin 7 structures, one in which the special submanifolds are the complex 2-dimensional complex surfaces, and the other where there's a special Lagrangian?
No, I said if we fix our Calabi-Yau 4-fold with a fixed form, we get a fixed spin 7 structure. And out of the class of all possible Cayley manifolds, there are 2 particular subclasses that we're familiar with. There could be other ones. There could be other kinds of Cayley manifolds for all we know. But they're just examples that we... The class of Cayley manifolds contains contains both of those particular kinds. So now we want to go down to 7 dimensions, which is where we're supposed to be for this meeting. I was considering G2 in spin 7, which corresponds to considering a 7-dimensional manifold Y with holonomy G2 and take its product with R, and then this 8-dimensional manifold would have holonomy spin 7. The structure on Y is given as we heard this morning by a 3 form, phi, which is related to our 4 form. So we have our 4 form, let's take t to be the coordinate on r. We have our 4 form, capital Phi. We write this as dt wedge phi plus the other component will always be the star of phi with respect to a particular metric determined by phi. So the upshot is that we get if we go down from 8 dimensions to 7 dimensions, we've now, considering these particular pair of forms, and this is just algebraically, the differential geometry, the fact that the holonomy is encoded in the fact that these are closed form. So we can say what happens if we looked at the things we were looking at before, but induced from y in natural ways. So first of all, we can take translation invariant connections, which actually there are, as we'll say again in a few minutes, or if not then tomorrow, there's 2 slightly different notions of what you could mean by that. But let's first of all mean that we have a connection. So we're A lifted from Y. We have a bundle and connection which we lift from Y. When does it satisfy the spin 7 condition? That just comes down to saying that F, the curvature, wedge star phi, is equal to 0. So we have a connection now. We have a bundle E over Y with a connection, let's call it, say, A0, let's call it. If we lift that up to a connection on the product, ask when do we satisfy those equations, it's just when back in 7 dimensions we satisfy this equation. So this is called the G2 instanton equation. And this actually corresponds to the same kind of, if we did the same, if we started off in the same way as we did before here, again, we would get the same picture that, in fact, we get lambda 2 of R7 is equal to the Lie algebra of G2, which is 14-dimensional, directs a 7-dimensional complement. So this is lambda. So again, it corresponds to setting the saying that the curvature of your connection lies in the part of the 2 forms corresponding to your holonomy group. Notice that automatically that means that if we take the Nevichivita connection, that will satisfy these conditions, because just from the way the definition of curvature works. In any case, that's an equation we can write down. We've written it down. We'll hear talks about it. Well, I'm going to say more about it, and we'll hear talks over the next coming weeks. What about the submanifolds? There are 2 things you could do. You could consider a 3-dimensional submanifold of Y, and then ask when is the product of that with R? When is that a Cayley submanifold? That leads to what's called associative submanifolds. We could give a definition, a purely 7-dimensional definition, if we wanted. Or we could say, supposing we have a 4-dimensional submanifold of Y, and we just include it in X by including Y as one time slice, then we get the notion of a co-associative submanifold. So submanifolds. So we can take a P3 in Y such that P times R is Cayley. So these are called associative. That's the definition. This is a definition. Another definition is to say that if I take star of phi and contract that with any vector v, any v in the tangent space of y at the relevant point, and I restrict that to the tangent space of p, that should be equal to 0. Or there are probably 101 other ways of writing down the definition. So, or we could say that P, or we could consider a four-dimensional submanifold in Y, and saying that, so this is contained in X as in an obvious way. This is Cayley if and only if Q is co-associative, again the definition. Which one can again characterize directly by saying that the restriction of the 3 form to Q is equal to 0. I think if I get it right. So there are two special kinds of submanifolds in our G2 manifolds that we've got. Let's keep on going one step further, because again this will give another model for G2 which is useful and will connect with various things. So let's consider now the inclusion of the group SU3 inside G2. That's to say, if we consider Y as the product of a 6-dimensional manifold Z with R, then Y will have holonomy G2, provided that Z has holonomy SU3. That's to say, it's a Calabi-Yau threefold. So we did 8 to 7, now we're doing sort of 7 to 6. If Y is equal to Z 6 times R, Z has holonomy SU3, that is a Calabi-Yau threefold. This is, well, in point of view of groups, we're saying that G2 SU3 lies inside G2. In fact, as mentioned by Spiro, if you take the quotient G2 over SU3, it's just actually the 6th sphere. So, well, more or less that's what this is saying, that once you've fixed a direction in your tangent space of your G2 manifold, the remaining symmetry is just the SU3 acting on a complement. So what happens then? So here we have what are forms phi. So here we have a Cayley form. And again, a holomorphic form, we call it chi. Under this, the way we build our structure on Y out of this is the obvious one that phi, if we take S to be the coordinate on R, phi is equal to like omega squared wedge ds, not omega squared, omega wedge ds, plus the real part of chi. So we can do the same thing. What are the translation invariant G2 instantons? What do they correspond to in terms of data on our Calabi-Yau threefold? They just correspond to connections where the curvature F satisfies two conditions. One is that the wedge product of F with this three form here is equal to 0, and the other is that the let's take the inner product of F with omega is 0. You can write this F wedge omega squared is 0 in the equivalent way of writing it. So this is the last we get to something familiar, at least for some of us. This is the same, just algebraically. This is saying is that the whole 0, 2 part of the curvature is 0, because multiplying by the real part of chi gives an isomorphism from the sort of the 0, 2 forms into the relevant piece. So this is equivalent to saying F02 is 0, which is equivalent to saying we have a holomorphic structure. Or more precisely, for those who are not, let's review this for those who are not so familiar, if I take my covariant derivative on a bundle over a complex manifold, I can decompose this into curly d and curly d bar parts in just the same way as you do for the ordinary derivative on functions to define the d bar operator. Saying that the 0, 2 part of the curvature is 0 says that d bar squared, this is F02 is 0, it's equivalent to this, and this is just the integrability condition. That's to say, if we define a sheaf by taking the local solutions of the sections of E with d bar A of S is 0, then that actually defines a locally free sheaf. And if you just look at any old A, it would be trivial, probably there'd be no solutions. But this is just the integrability condition in which there are an adequate number of solutions. So this is, I say, something we understand, at least in terms of more familiar geometry. We're talking about holomorphic bundles, compatible unitary connections. This is just the standard, it's called Hermitian-Yang-Mills equation, studied in the theory of holomorphic bundles, which by a well-known theorem of Uhlenbeck and Yau corresponds to what's called a stable holomorphic bundle. This is the Hermitian-Yang-Mills equation. So in sum, we can say that these things are something we can describe entirely in terms of algebraic geometry, at least in principle. They correspond to the stable holomorphic bundles over your Calabi-Yau manifold. Of course, saying anything about such things is another matter, but we'll maybe hear talks about what one can say about bundles over Calabi-Yau threefolds. Similarly, for the submanifold story, again, we can do two things. We can take let's just take the associatives. We can either look at associative, which is written as a surface times R. So the associative equation, again, we can consider, well, let's just say in the same way we get two different reductions in just the same way. We either get holomorphic curves, so sigma, the complex curve in Y. If P is the product of a sigma times R, then associative just means that sigma is a complex curve, or
sigma is Z from Z times R.
Z. Sorry, that's Z, isn't it? We got to Z. Yeah. So sigma is a complex curve in Z if and only if sigma times R is associative in Z times R. So if we do the other thing, we just include as a slice, then we get what's called special Lagrangian in Y. So similar to what we were considering before. Lagrangian submanifolds with respect to the symplectic form, for which this preferred 3 form restricts to the volume form. When did I who's the boss? When did I start?
Maybe
5 minutes. Okay. Oh, that's all right. This gives you a good time. So this gives us more or less our kind of list of objects we want to do. I haven't tried to say anything about them or why these are interesting equations, but at least we got the equations on the board. That's all. So let's just going to summarize. We had dimensions 8. Sorry, that's right. This should be Z. I'm sorry. Yeah. So another way of getting an associative is to take a special Lagrangian in your 6 manifold and just include it in. So I'm just going to say one more. I'm going to write on a table just summarizing what we've said first. So in 8 dimensions, we have spin 7 instantons. And then we had Cayley submanifolds, these 4-dimensional things. In 7 dimensions, well, initially we have these, we had these G2 instantons. And then we had these associative, so we'll see the things that are analogous, in the way I'm going to explain, to the G2 instantons are these associative submanifolds. I'm going to explain and then similarly in 6 dimensions we have these just holomorphic bundles, essentially, stable holomorphic bundles. And these holomorphic curves. But we actually had a bit more. You see, we also had here we had these other things. We had these co-associatives as well. And then here we had these special Lagrangians in here. So can we put something in? What is this kind of gauge theory that should correspond to these things in some vague sense, which will be explained more in the talk by Gonzalo Oliveira in a couple of weeks' time. Let me just say that and then finish. When we talked about the invariant solutions, actually let's go back to our y times r. There are 2 different ways you could say that. One would be in the strong sense that we said that our connection is lifted up from y. The other is that we have a bundle over y times r, and we lift the translation action to the bundle in a way that preserves the connection. If that lift is actually parallel, with horizontal with respect to the connection, it's the same thing we did before, but it needn't be. You can have another lift. So there's another kind of notion of when you do this dimension reduction, to not just get a connection on the lower dimension, on a bundle over the lower dimensional manifold, but also get an extra field, we'll call it the Higgs field. So you get a pair consisting of, say, A, U, where U is a section of ND. Essentially, this is just the component of the connection in the extra direction. You compare you measure how far the horizontal lift deviates. Right, the lift of the action deviates from the horizontal lift, and that gives you U. So you can write down a slightly more general equation than this, the one we wrote down, which we'll call the spin 7. So we call it the G2 monopole equation. So this is where, what is this? So we take the same thing. We take F, A, wedge, star phi. This is a bundle valued, what have we got? 2 and 4. This is a bundle valued 6th form. And then we write this is star of DAU. So this is for a pair of a connection and a Higgs field, satisfying this equation. So of course, setting U equals 0 gives us the previous situation. And there's a similar thing you can do going down. In fact, there are 2 different. It's more complicated. You can do similar things when you go down to 6 dimensions. So we can also, in our sort of panoply of equations, put in some other things here, G2 monopoles. And so Calabi-Yau monopoles we can put in here. Okay, that's a good place to stop. All we've done is written down, this is our playground of things we're going to talk about more tomorrow and in the later.